while that's coming up, our most striking observation to date is the powerful effect that solar light appears to have on killing the virus, both surfaces and in the air. We've seen a similar effect with both temperature and humidity as well, where increasing the temperature and humidity, or both, is generally less favorable to the virus. So let me illustrate with this first slide. If you look to the right, you'll see that term half-life with a bunch of timestamps on there. First, let me tell you what a half-life is. We don't measure the virus as far as how long it will live on the surface. We have to measure the decay of the virus in terms of its half-life, because we don't know certain elements. We don't know how much a person expectorates when he spits, right? When he sneezes, whatever the case may be. We don't know how much virus is in there. So that has a bearing on how long the virus is going to be alive and active. So we measure it half-life, because half-life doesn't change. So if you look at an 18-hour half-life, what you're basically saying is that every 18 hours, the life of the virus is cut in half. So if you start with 1,000 particles of the virus, in 18 hours you're down to 500, in 18 hours after that you're down to 250, and so on and so forth. That's important as I explain the rest of the chart. If you look at the first three lines, when you see the word surface, we're talking about non-porous surfaces, door handles, stainless steel. And if you look at as the temperature increases and as the humidity increases, with no sun involved, you can see how drastically the half-life goes down on that virus. So the virus is dying at a much more rapid pace just from exposure to higher temperatures and just from exposure to humidity. If you look at the fourth line, you inject the sunlight into that, you inject UV rays into that. The same effects on line 2 at 70 to 75 degrees with 80% humidity on the surface, and look at line 4, but now you inject the sun, the half-life goes from 6 hours to 2 minutes. That's how much of an impact the UV rays has on the virus. The last two lines are aerosols. What does it do in the air? We have a very unique capability. I was discussing this with the president prior to coming out. He wanted me to convey it to you on how we do this. I believe we're the only lab in the country that has this capability. But if you can imagine a Home Depot bucket, a 5-gallon Home Depot bucket, we're able to take a particle, and this was developed and designed by our folks at the NBAC. We're able to take a particle of the virus and suspend it in the air inside this drum and hit it with various temperatures, various humidity levels, multiple different kinds of environmental conditions to include sunlight. And we're able to measure the decay of that virus while it's suspended in the air. This is how we do our aerosol testing. We work with Johns Hopkins Applied Physics Lab, and we actually developed a larger drum to do actually more testing. That's 4 times the size of that. So this is the capability that we bring to this effort. So in summary, within the conditions we've tested to date, the virus in droplets of saliva survives best in indoors and dry conditions. The virus does not survive as well in droplets of saliva, and that's important because a lot of testing being done is not necessarily being done, number 1, with the COVID-19 virus, and number 2, in saliva or respiratory fluids. And thirdly, the virus dies the quickest in the presence of direct sunlight under these conditions. And when you look at that chart, look at the aerosol as you breathe it. You put it in a room, 70 to 75 degrees, 20% humidity, low humidity. It lasts, the half-life is about an hour. But you get outside and it cuts down to 1.5 minutes. Very significant difference when it gets hit with UV rays. Mr. President, while there are many unknown links in the COVID-19 transmission chain, we believe these trends can support practical decision-making to lower the risks associated with the virus. If I could have my next slide, and while that comes up, you'll see a number of some practical applications. For example, increasing the temperature and humidity of potentially contaminated indoor spaces appears to reduce the stability of the virus. And extra care may be warranted for dry environments that do not have exposure to solar light. We're also testing disinfectants readily available. We've tested bleach, we've tested isopropyl alcohol on the virus, specifically in saliva or in respiratory fluids. And I can tell you that bleach will kill the virus in 5 minutes. Isopropyl alcohol will kill the virus in 30 seconds, and that's with no manipulation, no rubbing, just spraying it on and leaving it go. You rub it and it goes away even faster. We're also looking at other disinfectants, specifically looking at the COVID-19 virus in saliva. This is not the end of our work as we continue to characterize this virus and integrate our findings into practical applications to mitigate exposure and transmission. I would like to thank the President, thank the Vice President for their ongoing support and leadership to the Department and for their work in addressing this pandemic. I would also like to thank the scientists, not only in S&T and the NBAC, but to the larger scientific and R&D community. Thank you very much.